Hi, everyone. Welcome to our case study. Today's case study is all about that methylation activity fan gauge on the Dutch test. So if you've ever been looking at the Dutch test, looking at your patient's results or maybe your results, and you see that little methylation activity and it's pointing high or it's pointing low and you don't really know what to make of it, this is a good case study for you. So we're talking about a young woman with anxiety and poor methylation activity. My name is Dr. Kelly Ruef. I'm a clinical consultant here at Precision Analytical. This is my Instagram if you want to find me on Instagram. And I've got a doctorate of naturopathic medicine from NUNM and a bachelor of science in biochemistry and cell biology from UCSD. So some of you have already seen some of my other case studies, my other webinars, and you already know that I really like biochemistry. So today we're going to get into the nitty-gritty details around methylation and methylation pathways, how our methyl donors are created. So if you've had questions about methylation or the methionine cycle or the one carbon metabolism, the folate cycle, this should be a fun presentation. So our learning objectives, what is methylation and why is it important? So we're going to start with the basics. And then we're going to jump into that Dutch complete case study with the young woman with the anxiety. And then we're going to talk about further workup when low methylation activity is found on the Dutch test report. So this includes additional labs regarding nutrient status, genetic testing, and then questions about diet and lifestyle. And I just want to note, so we're not going to go over the treatment recommendations for certain genetic results in this case study. That's a whole other topic. So we're going to save that for another day. So this case study focuses more on, all of the different biochemical cycles and pathways that are necessary to generate methyl donors, to support methylation in the body, and how we can use lab testing, genetic testing, how we can ask the patient questions about their diet, about their lifestyle, to kind of get an overall idea of their methylation capacity. All right, so let's start out really basic. What is methylation? We talk about it all the time. What is it? Methylation is a chemical reaction in which a methyl group gets added to a molecule. So imagine you have a protein and you just add this little methyl group to the protein. So you're methylating the protein. And this is what a methyl group looks like. We've got the carbon in the middle and then the 3 hydrogens attached to the carbon. What is our universal methyl donor? So in methylation, the protein gets methylated, but something has to provide that methyl group. And it turns out that SAM, or people commonly call it SAMe, is that universal methyl donor. So SAM is the one that comes over and says, oh, here's a methyl group. And an enzyme says, thanks, SAM. I'm going to take that methyl group and put it on that protein. So SAM is S-adenosyl L-methionine, or SAMe. And why is methylation important? Now, why do we have to methylate proteins? Why do we methylate DNA? So methylation is happening everywhere. Like as we are sitting here right now, we probably have a bajillion methylation reactions happening in our body. They're happening all the time. They are turning on and off genes. They're helping with our hormone detoxification. They're helping us produce energy, ATP, helping with protein function, helping to make neurotransmitters and also metabolize, clear out neurotransmitters, help with overall growth and metabolism, DNA repair. It's amazing. Even muscle contractions. So most of those methyl groups that SAM carries around go to regenerate or to create creatine, which helps with muscle contractions. And I just put a little picture of a little baby here. So Methylation is very important for fetal development. It's just really great for growth overall. And this actually is a little photo of my baby. So there she is. Just wanted to share some photos of her. She's actually 9 months old now, and that's her right now. But methylation is crucial for human growth and development, but also crucial for a number of other things. So here's an example of DNA methylation. So we have our DNA, and one of these DNA methyltransferases, right? They're going to transfer a methyl group. So one of these little DNA methyltransferases, they're enzymes. They come over and they take a methyl group from Sam and they say, "Thank you, Sam. I'm going to put this methyl group on DNA." And in general, when you methylate DNA, you kind of shut down the DNA so it doesn't get expressed. So here we can see DNA methylation regulates gene expression by recruiting proteins involved in gene repression or by inhibiting the binding of transcription factors to DNA. So remember those transcription factors bind to DNA when they want to make some RNA, when they want to make a protein or they want to express the DNA somehow. So it kind of shuts that down. So methylation, very, very important for epigenetics. In epigenetics, we can turn genes on and off. So we have our genetic blueprint, but it doesn't mean that that genetic blueprint isn't the end all be all. We still have epigenetics. We can still change our lifestyle and our diet in such a way that we express the genes in a certain way for better or for worse. Okay, here's another example, and this is the one that comes up on the Dutch test. This is phase 2 estrogen detox. So remember, methylation is involved in phase 2 detoxification. And here, on the Dutch test, we measure 2-hydroxyestrone. This is a phase 1 estrogen metabolite. And we've got COMT or COMT. This is the enzyme that takes the methyl group from Sam and says, "Thank you, Sam. I'm going to methylate 2-hydroxy-E1 and turn it into 2-methoxy-E1." So this is the methylated phase 2 metabolite. And remember, the phase 2 metabolites, they're more stable, they're more water soluble, they're ready for excretion. The 2-methoxy-E1 even has some anti-cancer properties. So we want methylation to be occurring appropriately, right? Because the 2-hydroxy-E1, it's a phase 1 metabolite. And phase 1 metabolites tend to be a little unstable, a little rowdy. They can cause oxidative damage in the body. They can cause DNA damage. So we want to methylate them. We want to make them more stable. And COMT, this is catechol O methyl transferase. And remember the 2-OHE1, it's a catechol estrogen, just like the 4-OHE1. That's a catechol estrogen. And some people ask, "Oh, what makes it a catechol?" And you can see it here. So this little group is what makes this a catechol. It's got this little benzene ring, and we've got 2 hydroxy groups on it. So that's a catechol. So some of our neurotransmitters like dopamine, adrenaline, norepinephrine, those are catechols also. And interesting enough, we'll see COMT can help process and metabolize our dopamine and our norepinephrine and epinephrine or adrenaline. All right, now it's time for the Dutch case study. Let's introduce Jane. This is Jane. She's out in a flower field. She says, "Inspire others every day." She's just a very positive person, but she does struggle with a lot of anxiety. She's in her early 30s. She's a white female at ideal weight. She's got these irregular cycles and she's been diagnosed with PCOS. So we often see irregular cycles with PCOS. She struggles with anxiety and PMS, so a lot of mood issues. And she supplements with chaste tree berry, probably using that to help regulate her cycles. Remember, chaste tree helps with ovulation and progesterone production. Magnesium, inositol, NAC, and some desiccated beef liver. So let's look at her results. This is page 1 of a Dutch complete. This is more of a summary page. And so we can see some of the kind of important markers side by side here. What I like about page 1 on a female report is we can see the most potent estrogen, estradiol, right next to the progesterone. And on page 1, we have the calculated serum equivalent for progesterone. And her serum equivalent is 15.4. That looks great. I love to see progesterone around 15, especially for fertility. For fertility, I like to see around 15, 20. But we can see here her estrogen dial is above range. It's in the red. So she's got some estrogen excess. And on page 1, you can also see the key on how to read the results. So remember the little purple band down here, that's the postmenopausal range. And in between the two stars is the luteal range. So we want women to collect in their mid-luteal phase. And of course, you'll see testosterone, DHEA, the cortisol metabolites, they don't have a little purple band. So they don't have a postmenopausal range. And they just have 2 stars. And the 2 stars is the overall range for all the ages. All right, so we go down to page 3. We can see her progesterone metabolites, the alpha and beta pregnenolone. We can see her estrogens down below. So her parent estrogens, E1 and E2, and then some of these estrogen metabolites. And then the androgens on the top left. And remember, estrogen excess can contribute to mood disturbances and PMS. So, her symptoms could be in part due to this estrogen excess. So the progesterone metabolites are within range. And remember, when a woman isn't supplementing with progesterone or pregnenolone, the urinary progesterone metabolites strongly correlate with serum progesterone. So she probably has some great looking progesterone during her luteal phase. As we said before, her E1, her E2 are above the luteal range. Her estriol, though, is still within the luteal range, maybe getting a little towards the higher side. And urinary estradiol strongly correlates with serum. So if we look down at her estrogen metabolism patterns, these 3 here, the 2-OH, the 4-OH, and the 16-OH, these are phase 1 estrogens. And on page 3, we show the estrone metabolites. So 2-hydroxyestrone, 4-hydroxyestrone, 16-hydroxyestrone. And remember, we label them the good, the bad, and the ugly. So the good, the most stable pathway is this green pathway towards the 2-hydroxyestrone. The bad, or the equivocal, is the 16-hydroxyestrone. 16-hydroxyestrone is a proliferative estrogen. So if it gets too high, some women might have breast tenderness or heavy bleeding. If you already have an estrogen receptor positive cancer, we wouldn't want this one to be high. It's going to make that cancer grow. But the 16-OH1, because it's proliferative, also helps with bone mineral density. So it's not all bad, right? Just want it in balance. And then the ugly is the 4-OH-E1. This is the red pathway. We don't want much estrogen going down this pathway because the 4-OH-E1 in the research is the one we worry about most becoming this reactive quinone and causing DNA damage and increased risk for breast cancer and endometrial cancers. So remember, phase 1 estrogen metabolites, they're all a little rowdy, a little unstable, can cause DNA damage, oxidative damage in the body. We don't want them to be hanging around phase 1 for too long. We want them to be methylated, glucuronidated, sulfated, N-acetylation or N-acetylated, I'm not sure how you say that one, or conjugated with glutathione. So all of those are phase 2 reactions to help move those unstable phase 1 metabolites over to phase 2, where they're more stable, more water soluble. So the 2-methoxy-E1, that's the phase 2 metabolite. So you can see here, her 2-hydroxy, her 4-hydroxyestrone, both of these dials are above range. I don't like to see that, right? Because they can cause oxidative damage in the body and DNA damage. The 4-OH will cause more DNA damage than the 2-OH, though. The 4-OH forms these unstable bonds with DNA, whereas the 2-OH forms stable bonds with the DNA. So the 4-OH puts you at more of an increased risk for that DNA damage and the breast cancer. So these dials are above range. Don't like to see that. And if we look at this pie chart here on the right, this tells you percentages of each of the phase 1 estrogens. So how much estrogen is in the 2-OH form, how much is in the 4-OH form, and how much is in the 16-OH form. And I kind of blew up the pie chart over here on the left so we can see it more easily. And her percentages look great. Like she's pushing most of her estrogen into the 2-OH form, and the 4-OH form is less than 11%, and the 16-OH is below 30%. So I'm pretty happy with these percentages. It's just her dials, her 2-OH, her 4-OH are above range because her parent estrogens, her E1, her E2 are above range. So she's got estrogen excess, but at least she's pushing down each of the phase 1 pathways adequately or appropriately. And we can see here her methylation activity is low. So this little red dial is pointing to the left towards low. And with this methylation activity, we're comparing the 2-hydroxy-E1 number, so 20.4. We're comparing that to the 2-methoxy-E1 number, the 6.83. So in phase 2, the 2-hydroxy-E1 and the 4-hydroxy-E1, they both can be methylated. So it's really important for methylation to be working well, because if methylation is low, then the 2-hydroxy-E1 and the 4-hydroxy-E1 can back up and build up in phase 1 and cause more DNA damage. So how is the methylation activity on the Dutch fan gauge determined? How do we determine where this red dial points? It turns out the methylation activity fan gauge represents the ratio between that 2-methoxy-E1 number and the 2-hydroxy-E1 number. So let's start with the middle one here. If the red dial is pointing straight up, that means 2-methoxy-E1 is exactly half of 2-hydroxy-E1. If 2-methoxy-E1 is more than half, the red dial will point to the right and will have higher methylation activity. But if the 2-methoxy-E1 number is less than half of the 2-hydroxy, so not much is going into 2-methoxy, then we'll have the low methylation activity. That little dial will point to the left. And with Jane's results here, so let's calculate it. The 2-hydroxy-E1 number is 20.4. Okay, what is half of 20.4? It's 10.2. So the 2-methoxy-E1, the 6.83, is that less than 10.2 or more than 10.2? It's less, right? So that's why this red dial is pointing to the left. So she's got low methylation activity. I usually like to see this red dial pointing straight up or to the right. So I would want her number to be at least 10.2 for 2-methoxy-E1. So she's not moving enough estrogen from the 2-hydroxyestrone form, phase 1, over to the 2-methoxy-E1 form, phase 2. So does this mean that Jane has low methylation activity in her entire body? Not necessarily, but it can give us an idea of methylation activity in the body. So remember, this little fan gauge here, it's based off of just 2 estrogen metabolites in the urine. So it can give us an idea of methylation activity in the body, but there's other things we can do, which we're going to talk about, to try to understand the entire methylation activity in the body. So remember, we just talked about this, but I'm going to bring in Sam here. So remember the 2-hydroxy-E1, this is our phase 1 metabolite. the COMT enzyme comes around, and COMT takes a methyl group from SAM and says, thanks, SAM, and methylates 2-hydroxy-E1, turning it into 2-methoxy-E1. And if we look at the estrogen metabolism pathways, we can see here that we want estrone to be metabolized, into the 2-hydroxy-E1 and the 4-hydroxy-E1, but we want these to be methylated to 2-methoxy-E1 and 4-methoxy-E1 and excreted from the body. This is a big thumbs up. This is good, right? This is good. So we want methylation to be working well. What we don't want is for the 2-hydroxy-E1 to become a reactive quinone, or for the 4-hydroxy-E1 to become a reactive quinone and cause DNA damage. The 4-hydroxy gets 2 thumbs down because it causes more damage than the 2-hydroxy-E1. That gets 1 thumbs down. And I did a whole case study on the 4OH and breast cancer risk. Definitely check it out. Here is the link. Just type it into your web browser. If you want to learn more about 4OH and breast cancer risk and what you can do, all the questions you can ask, different treatment options for if 4-hydroxy is elevated. So how can we get a better idea of the methylation activity in her entire body? Let's talk about this soon, I promise. But let's finish going through Jane's results first. Okay, so back to page 3 of her Dutch Complete. On the top left, we can see some of these androgen metabolites. We've got testosterone. We have the sulfated form of DHEA. So the sulfated form is more stable than DHEA, the unsulfated form of DHEA. The sulfated form of DHEA has a longer half-life. So it can float around in circulation and it can just stick around longer than just DHEA. So we want to make sure that we have enough kind of in this circulating kind of storage form. And then DHEA can be metabolized downstream into etiocalanolone and androsterone. And so if we look at her DHEA metabolites, for her age, they look great. And actually, let's see, etiocalanolone. Yes, so I highlighted the 40 to 60 age range, but she's actually in her early 30s. So we should be looking at the 20 to 39 age range. So just want to make that correction. And her testosterone, it's within range for her age, little on the high side. And we can see here her 5-alpha reductase activity fan gauge. Her little red dial is pointing slightly over to 5-alpha preference. Remember, if you favor 5-alpha, then you tend to push your androgens down 5-alpha reductase into these more potent androgenic metabolites. So when I say more potent, I mean that they're more likely to cause acne or facial hair growth or body hair growth or scalp hair loss or mood issues. So these symptoms of estrogen excess. And in PCOS, in the research, we see that women with PCOS tend to favor the alpha pathway. It's probably because inflammation, stress, and blood sugar dysregulation tends to push the alpha pathway. So if you go back to page 2, we have a few downstream testosterone metabolites here that are on page 2. They're not on page 3, so always go back to page 2. And they look pretty normal. Her 5-alpha androstenediol is a little above range. But remember, 5-alpha DHT, that's our most potent androgen. It's the active form of testosterone. And 5-alpha androstenediol might be a pretty good marker of androgenic activity in the tissues. So her androgens overall kind of going, a little on the higher side. And we know that higher androgens can aromatize over to estrogen. So sometimes you see higher estrogen in the tissues due to higher androgens. All right, let's look at her adrenal panel. So this is her adrenal panel here. This is page 5 of a Dutch Complete. And on the top right, we can see her total DHEA. For her age, we want it between 1,300 and 3,000. She's within range. That looks good. Her metabolized cortisol, This tells you total cortisol production, and she's within range. And then if you look down here, these two graphs represent cortisol, active cortisol, and inactive cortisone. So they kind of represent, they give us an idea of cortisol in circulation, free cortisol in circulation. And both of them, she's got a diurnal pattern. Overall it's higher in the morning, lower at night, but it's not very pronounced. Her cortisol, her total cortisols, free cortisol in circulation is low normal. So some kind of normal low cortisol there. And if we look at her organic acids panel, here we go. We can see that the very first one here, this is methylmalonate. If methylmalonate elevates in the serum or the urine, it's usually due to a low adenosylcobalamin, kind of low B12, because methylmalonate needs adenosylcobalamin to be converted to succinyl-CoA. So if there's not a lot of B12 around, MMA can back up in the urine and the serum. You can do this test in the serum too. So hers is on the high end of range, which means she could be low in B12. And we definitely know that B12 is important for methylation. We'll talk about that more. And then her dopamine metabolite, her homovanillate, is on the low end of range. So the metabolite in the urine is on the low side. But when it comes to her symptoms, seems, she's got a lot of anxiety. She actually might have high dopamine in her body. And remember, dopamine is a catechol, and it gets metabolized by that COMT, the catechol O methyltransferase enzyme. Remember that? So COMT finds dopamine and helps to metabolize and clear it out of the body. But if she's got low methylation activity, if she has a sluggish COMT enzyme, her dopamine might build up in her body. Same with her adrenaline. Adrenaline gets methylated and cleared out of the body. So they could build up in the body and be high in the body, but low in the urine because they're not being methylated. They're not being cleared out well. So I have a suspicion for that. And then her melatonin, a little on the high side. You can see that with sometimes people eat some foods that are higher in melatonin during testing, like pistachios or cherries are a big one, corn. Sometimes it's normal. People just make a little more melatonin. But I also think about gut health because a lot of melatonin is made in the gut. All right, so here are symptoms of low dopamine and symptoms of high dopamine. And symptoms of high dopamine some of them can overlap with symptoms of high adrenaline. And she's got more of these symptoms of high dopamine. So I suspect her dopamine is building up in the body and it's not being methylated. It's not being cleared out well by COMT. So she's got that low methylation activity. It makes sense. So remember, dopamine, norepinephrine, and epinephrine, also known as adrenaline, get metabolized via the COMT and also MAO. MAO plays a part in the detoxification also. If someone has SNPs that slow down COMT or MAO activity, then the body may have more difficulty metabolizing and clearing out dopamine and other catecholamines. In these cases, we may see low dopamine metabolites in the urine, but in the body could be higher. Also, here's another key point. Elevated estrogen has an epigenetic slowing effect on COMT and MAO. So remember, she has high estrogen, and it could be slowing the clearance of her neurotransmitters, causing the higher dopamine and adrenaline in her body and higher anxiety. So supporting methylation, supporting estrogen detoxification might actually improve her mood. It's worth a shot, right? Okay, summary of findings. So we found low methylation activity, slightly low cortisol, And, cortisol can play a role in mood too. Slightly low dopamine metabolite in the urine. So I'm wondering, possibly high dopamine in the brain or in the body. And then possibly low B12. Her MMA was on the high side, remember? Normal. Within range progesterone, her progesterone looked great. Within range total DHEA, her DHEA looked great. She did have a few high findings. Remember, her androgens were on the high side. She had that 5 alpha preference, high estrogens, the high phase 1 metabolites, the 4-OH and the 2-OH. A little, her melatonin was a little on the high side. Yeah, maybe that high dopamine in her body. All right, so where did we leave off? I promised we'd get back here. So how can we get a better idea of the methylation activity in her entire body? This is a really good question. Let's see if we can answer it. So there's additional labs regarding nutrient status. So remember, in order to make SAM, which is our universal methyl donor, we need certain cofactors, we need certain amino acids, we need certain nutrients. Genetic testing. So also to make our universal methyl donor, SAM, we need certain enzymes. We need certain enzymes to be functioning to help create SAM. And then we can ask questions about diet and lifestyle, which will give us an idea of nutrient status, really. Is she eating foods high in folate? Is she really stressed out or drinking alcohol and depleting her B vitamins? So those are some examples. All right, so let's talk about how SAM is made, because we really have to understand how we make SAM and what we need to make SAM before we can understand what genes to test for SNPs or what nutrients to look out for. Okay, so we will go through this step by step, but this is just an overview. This shows, one carbon metabolism. We've got the folate cycle. We've got the methionine cycle. But see here, this little purple, this is SAM. This is how we create SAM in our bodies. And this is happening all the time. These cycles are taking place right now in our bodies. Pretty cool. Okay, let's start with folic acid. So we've heard of folic acid, right? It's the synthetic form of folate. And we know that if we take folic acid, it has to convert all the way down here to 5-methyl THF. This is the active form of folate. This is the form of folate that we need in order to make SAM. So if we get dietary folate, if we get folate from our vegetables, our green leafy vegetables, a lot of it already comes in the 5-methyl THF form. And when you take an active B complex, a lot of times it has the 5-methyl tetrahydrofolate form in that B complex. All right, but let's start up here with folic acid. So folic acid gets converted to dihydrofolate, DHF, and then DHF is converted over to tetrahydrofolate, THF, by dihydrofolate reductase. And the DHFR gene encodes for dihydrofolate reductase. So this part of the cycle, I don't know, it's kind of boring to me. It'll get more exciting, hopefully. All right. So now we have, let's see if I can pronounce all these, methylene tetrahydrofolate dehydrogenase. That's encoded by MTHFD1. So right here, this enzyme, it helps convert that tetrahydrofolate over to 5,10-methylene tetrahydrofolate. It's the MTHFD, or the methylene tetrahydrofolate dehydrogenase. It's a trifunctional enzyme. So it's actually catalyzing a few different chemical reactions to get THF over to 5,10 methylene THF. And I kind of zoomed in to exactly what MTHFD does in case you're interested, like how does it get THF over to 5,10 methylene THF? It does all of these reactions. That's crazy. It's a trifunctional enzyme. But you probably don't really need to know this part. It's not that exciting. Okay. So, there's another way that tetrahydrofolate can convert over to 5,10 methylene tetrahydrofolate. And that's through the serine hydroxymethyltransferase enzyme encoded by SHMT. And SHMT, what it does is it takes a methyl group from serine. So it says, thanks, serine. And it takes that methyl group and puts it on tetrahydrofolate, turning it into the 5,10 methylene tetrahydrofolate. And serine, since it loses a methyl group, it turns into glycine. And then the 5,10 methylene tetrahydrofolate, it it can go over here and help with DNA synthesis and repair. So it can donate, basically it can donate a methyl group over here and turn this uracil into is it thymine? Thi, thi, I'm blanking on that right now. But anyways, it can help with DNA synthesis and repair. Or the 5,10 methylene THF can convert over to 5-methyl THF. And remember, 5-methyl THF, this is the form we need. This is the active folate that we need to make SAM. And so the 5,10 methylene THF gets converted by this enzyme, methylene tetrahydrofolate, encoded by MTHFR. So this is the pretty famous gene right here, right? We're always looking at SNPs and MTHFR. So it has a cofactor of B2, and it converts the 5,10 methylene THF over to 5-methyl THF. So now we've got the folate in the active form that MTR can use to eventually make SAM. And the MTHFR, we can look at the SNPs here. And the SNPs, so what does SNP stand for? Single nucleotide polymorphism. So the SNPs that are most common that we look at for MTHFR, where there can be issues in slowing down enzymatic activity, is the 677. This is just the place where you find it in the gene. So the 677 and the 1298. And you can see the enzymatic activity. So if we're wild type, if we don't have any SNPs, then we have 100% enzymatic activity. And I believe the 677 SNPs can affect function more so than the 1298. But you can see here, I mean, when we get down towards the lower end over here, when we start having more, more frequency of these SNPs, we don't find them that often in the public, and it's probably because people tend to have a lot of issues if they're not methylating well. And a lot of these are just not compatible with life. So if someone has certain SNPs, which puts them in this category down here, it might not be compatible with life, and they might not even make it through the pregnancy. This is interesting. So the MTHFR 677TT genotype is associated with an increased risk for heart disease, stroke, hypertension, preeclampsia, neural tube defects, and elevated homocysteine. So methylation, it really does matter. If you're methylating well, it can affect your overall health. All right, so we've got the folate in the active form, right? The 5-methyl THF form. And now what happens is methionine synthase, which is encoded by MTR, it's going to convert homocysteine to methionine. But the folate, so this active folate here, it donates the methyl group to methionine synthase so that methionine synthase can methylate homocysteine and turn it into methionine. And methionine synthase, this MTR, it uses B12 as a cofactor. So MTRR, so this is methionine synthase reductase. And methionine synthase reductase, its job is to convert methionine synthase from its inactive form to its active form. And how does it do it? It makes sure that B12 is in the form that methionine synthase can use. So MTRR, or methionine synthase reductase, it keeps B12 in its active form so that methionine synthase can be activated, and so that methionine synthase can take the methyl group from our active folate and put it on homocysteine, converting it to methionine. And then methionine eventually is going to be converted to SAM, which is our universal methyl donor. All right, so there's another pathway that I added in here. There's another pathway that can convert homocysteine to methionine, which is nice, right? If you've got a ton of SNPs in MTR, MTRR, MTHFD1, if you got a ton of SNPs over here, it's probably a good thing that we have an alternate pathway to help move homocysteine over to methionine. Because remember, homocysteine, if it backs up in your body, if it gets too high, it causes endothelial damage. It's going to increase risk for cardiovascular disease, pregnancy complications. Just think about the placenta. It's a super vascular organ, and homocysteine can damage the placenta. So we don't want high homocysteine. We want to make sure this methylation, the methionine cycle, is working well, so that we don't have a bunch of homocysteine going around causing havoc on our blood vessels, on our vascular tissue. So this is called the BHMT betaine methylation pathway. And this enzyme, betaine homocysteine S-methyltransferase, encoded by BHMT, it takes a methyl group donated by betaine and converts homocysteine to methionine. And it uses a lot of cofactors here. So then you ask, okay, betaine, what is betaine? How do I get betaine? Well, another word for betaine is TMG, or trimethylglycine. They're the same thing, just another name. Choline is a precursor to betaine. So choline gets irreversibly oxidized to betaine in the mitochondria. So we also need good mitochondrial function for this. Choline, most people, when you look at the research, most people are not getting enough choline in their diet. And it's probably because a lot of people aren't eating a lot of eggs and they're not eating animal liver. Remember, animal liver is a great source of choline, but a lot of people just aren't eating those. Other sources are salmon, pinto beans, some seeds, but they're not as rich in choline as the egg yolks and the animal liver. But basically, choline converts to betaine. You can also just get betaine from the diet. Betaine, you find it in beets, you find it in spinach. It's a few different places. Actually, there's a really good resource I love. Chris Masterjohn, he has a PhD in nutritional sciences. He has a website, and if you type in Chris Masterjohn choline database, he talks all about choline and betaine, where you can get it in the diet, supplementation. It's a great resource, so check it out. All right, so for this, we need zinc, B2, B3, B6. We want to probably get some choline in our diet or supplement with it. Get some betaine or TMG in our diet. This just shows you how choline converts over to betaine. And then betaine donates that methyl group to BHMT, and BHMT says, thanks, betaine. I'm going to take that methyl group, put it on methionine. And then methionine turns to SAM. You can make choline in other ways too. So the PEMT, the phosphatidyl ethanolamine N-methyltransferase, this can actually make phosphatidylcholine. And it's interesting because in order for the PEMT or PEMT to make phosphatidylcholine, it actually needs a methyl group from SAM. So it relies on SAM, the universal methyl donor, to create choline. And sometimes people have SNPs in the PEMT gene, which slows this activity. So they're not as able to make choline de novo, or just making choline in the body from scratch, basically. So it might set people up with more of a choline deficiency. And there's research that SNPs and PEMT, but also the MTHFD1, I think I said that right. Both of those, if there's SNPs in those, you can have a choline deficiency. So it might be a better idea to get more choline from the diet. And probably good to space the choline out throughout the day. There is some concern about if you eat too much choline at once, like if you had 6 or 7 eggs all at once, maybe some of that choline can convert to TMAO, which is not great for the cardiovascular system. So I tend to have people space it out throughout the day if they're taking choline. All right, so after going through all of those pathways, hopefully we understand these cycles a little bit better, and we understand what nutrients are needed to make that universal methyl donor. That wasn't so bad, right? Hopefully you're following. I know it can be super complicated, but all you have to do is like teach it to 10 people, maybe 100 people, and then you get it down, right? But so we need B12, folate, B6, B3, B2, zinc, magnesium, iron, potassium, amino acids, choline, betaine. We need all of these nutrients in order to make SAM, in order to support methylation. So additional labs, we might want to look at homocysteine. This would be like my number one go-to test. When I'm trying to understand methylation capacity, I'd probably look at homocysteine. Because remember, if homocysteine is elevated, it's probably because it's backing up in the body and it's not being converted over to methionine and to SAM. So if homocysteine is elevated, it might mean that there's low methylation activity. And it might mean that, we just don't have those cofactors to turn homocysteine over to methionine and SAM. So we might be low in B2 or B3 or B6 or folate or B12 or zinc. B12 status, we can look at serum or urine MMA, methylmalonate. This is pretty good lab. It's pretty good at telling us if we are low in B12. You can also look at serum B12, but the research says the serum B12 isn't really clinically useful unless it comes back low. If it comes back low, then they've got low B12. But if it comes back normal or high, then you still don't really know about the B12 status in the cell or the activity of the B12. And that's where MMA comes in. That's where MMA is better. Folate status, so we can look at folate in the RBCs, the serum, FIGLU. This is an organic acid in the urine. If it elevates, then folate can be low. And you can even look at the uracil-thiamine ratio in the urine. So remember, the folate donates that methyl group to uracil, turning it to thiamine. So if you've got more uracil to thiamine, if you've got a higher ratio, it could mean that you've got lower folate, right? We want to look at a CBC just to look for anemia. That could be important. If you're low in B12, you can have anemia. If you're low in iron, you can have anemia. It can be another measure, marker, another way to try to understand the nutrient status of the person. And then an iron panel. B6 status, so one way is to look at these organic acids, the xanthuronate and the kynurenate in the urine. And we actually measure these on the Dutch test. So this is great. We can look at the B6 status on the Dutch test. Hers look good, remember? And then micronutrient testing. Micronutrient testing, you can look at the B vitamins, the minerals, the amino acids, choline. So SpectraCell is a great company that looks at micronutrients. Genova, they've got like the NutriEval. So there's a few different ones on the market. And then methylation panels. So some companies offer methylation panels, and usually they're looking at nutrients, but also some genetic SNPs. So Vibrant Wellness has a methylation panel. Genova has a methylation panel. These are some things to look into. And of course, we can look at some other nutrients in the RBCs or the serum. So one note about homocysteine, I think I said this before, but elevated homocysteine, it's an independent risk factor for coronary artery disease, stroke, peripheral vascular atherosclerosis, and arterial and venous thromboembolism. So when homocysteine goes up, it causes endothelial damage. It damages the vascular tissue. So we don't want homocysteine to elevate. If it's elevated, we're probably going to support the B vitamins. We're probably going to support choline, right? So the optimal range, this is kind of like the functional range, but the optimal range is likely somewhere between 5 and 9. And it has to be fasting. Make sure you're fasting when you do the homocysteine. We don't want homocysteine to be too low, right? Just think about it. If you don't have enough homocysteine, then you don't have enough substrate to make SAM. Also, homocysteine converts down to glutathione. So if you don't have enough homocysteine, you don't have enough homocysteine substrate to turn into glutathione, which is our major antioxidant in our body. So homocysteine, they rise with low B12, low folate, low B6 deficiencies, hypothyroidism, some renal issues, some medications, and lifestyle factors. So we can kind of, we can look at the methylmalonate on the Dutch test to evaluate B12 status. We can look at the xanthurnate and the kynurenate on the Dutch test to evaluate B6 status. So if I have a patient with high homocysteine, but on their Dutch test, their methylmalonate looks good, their xanthurnate, their kynurenate looks good, I'm going to start thinking folate deficiency. I'll probably go check their thyroid too. And then here, this just shows you that homocysteine converts down to glutathione. All right, so genetic testing, if we go back to the pathways, if we take out all of those genes, these are the ones, these are the genes we're going to look for. COMT, remember, this is going to help methylate a lot of different things in our body, but it's going to help methylate dopamine, adrenaline, the 2-OH, the 4-OH estrogen catechols. It's going to help methylate those catechols. And then these two, we can look at these to evaluate B12 absorption ability, B12 transportation ability. So you can also ask about questions about diet and lifestyle. So, are you eating foods rich in B12? Are you eating these foods? A lot of these foods, like the salmon, I think the beef, the eggs, they are, especially beef liver, they're high in choline too. So are you eating foods rich in folate? What about choline and betaine? Betaine is in the spinach and the beets. Eating foods rich in B6, B2, B3, zinc, magnesium, iron. You could do a quick Google search and figure out what foods those are highest in. Are you stressed out? Drinking alcohol? Those deplete a lot of key nutrients needed for methylation. So do oral contraceptive pills. So this is actually study, and it shows that the OCPs, they deplete folic acid, vitamins B2, B6, B12, vitamin C and E, and minerals, magnesium, selenium, and zinc. And when I read that, I was like, oh my gosh, those are almost all of the nutrients needed for methylation. So if you're on an oral contraceptive, watch out for your methylation. Maybe think about multivitamin, a B complex, getting more of these in your diet, So here's a sample treatment plan for Jane. Remember, she is in her early 30s. She's got that higher estrogen, right? She's got the higher 2-OH, the higher 4-OH, and she's got anxiety and PMS. So we want to support methylation, and we want to help lower estrogen. And when we support methylation, we're going to help clear out the estrogen. So when you support methylation, it's going to help clear out the 2-OH and the 4-OH. It's going to help clear out the estrone, the estradiol. So hopefully by supporting methylation, that's going to help lower, help with the mood issues. All right, so here's some extra testing, CBC, CMP. We're going to look at her blood sugars, because usually with PCOS, it's the dysregulated blood sugars and the high insulin that can lead to elevated androgens and oftentimes leads to, in effect, elevated estrogen. I'm going to do a SpectraCell micronutrient test just to see where her nutrients are, her nutrient status. And then I'm going to do a Max Gen Labs, the Works genetic test. Talk a little bit more about that. And have her continue these. These can be great for PCOS. Remember, inositol can help regulate blood sugars and help lower the testosterone. NAC can help make glutathione, great antioxidant. There's a lot of research around NAC and PCOS. And the desiccated beef liver, guess what that has? It has a little bit of B vitamins, but it has some choline too, a little bit of choline. And then I'm going to start the active B complex. So we want to get more B vitamins in the diet to support methylation. And switch the magnesium to a magnesium chelate powder. This is going to have more of the glycinate form. And remember, magnesium not only helps with methylation, but it also helps with DNA repair. And her 4OH is elevated. I don't like that because that 4OH can cause DNA damage. So the magnesium hopefully will help her repair any DNA damage. And then increased consumption. So all of these here, they contain choline, they contain betaine, so they're going to support methylation. But like the rosemary helps block the 4OH pathway. The cruciferous veggies, carrot family veggies, those are going to help push the healthy 2OH pathway in phase 1. And then the broccoli sprouts. Broccoli sprouts are great. They just support phase 2 in general because they increase the transcription of phase 2 enzymes. But they also activate glutathione pathways. So they're going to help with antioxidant status in the body. But some of these, they're also going to have B12 in them. They're going to have other nutrients that we need to support methylation. So this is this is kind of some of the genes that the Max Gen, the Works panel tests. And all of the genes that we listed before, it tests. It looks at various SNPs of all these genes. And on top of it, it also looks at CBS, which can help move homocysteine over to glutathione eventually down that pathway. CYP, 1A2, 1B1, these are enzymes involved in phase 1 estrogen detox. Pretty cool, right? So CYP1B1, remember, this is the enzyme that converts estrone or estradiol over to the 4-hydroxy metabolates. So you can always evaluate that for people to see, are they genetically susceptible to pushing more down that 4OH pathway? We can look at some glutathione genes, the MAO. Remember, MAO helps to clear out dopamine and adrenaline. So if these are slow, they have SNPs. Genetically, we might do things to support MAO just to help clear out the dopamine, which might help with the anxiety. And then we also have some genes around SOD, which is more antioxidants. And what I like about the Works panel is we have just it's easy to read. The information, they lay it out in a really easy to read. Like, I could give this report to my parents and they could understand it, which is great. All right, so this protocol aims, number 1, we're going to support healthy estrogen metabolism and clearance. So we're going to support methylation and support COMT to help clear out those estrogens. And that's going to minimize risk for cancer like breast cancer and endometrial cancer, but it's also going to hopefully help with the PMS and the anxiety. We're going to support healthy neurotransmitter metabolism and clearance. So remember, that's going to be supporting methylation, supporting COMT to help clear out dopamine, help clear out adrenaline. Reduce potential for quinone DNA damage. So remember, when you support methylation, you're just helping to clear out the 4OH and the 2OH metabolites. And it just helps keep them so that they don't spend as much time in phase 1 and they don't have as much risk to turn into a reactive quinone and cause DNA damage. We're going to work up some common causes to higher T. Basically, I'm going to check in on her blood sugar at this point. and look into genetics and nutrient status. So the MaxGen report is going to help us understand her methylation capacity. Might help us understand if she is genetically susceptible for being deficient in folate or deficient in B12, um, or low, SNPs in COMT, or SNPs in MTR or MTRR. And it's going to help us understand her antioxidant capacity. Remember, there's SNPs around SOD and glutathione. Even how she's able to regulate blood sugars. So hopefully improving these will improve the estrogen clearance, the neurotransmitter clearance, help her anxiety, her PMS, might even give us some tips on how to regulate her blood sugar and what exercises she should do to best help her her overall health. Okay, that's it. Thank you so much. I hope you learned something new. I hope I have made those cycles in the methylation overall a little bit easier to understand. If you have any questions, feel free to email info@dutchtest.com. All right, have a great day. Bye-bye.